Okay, this video lesson is dealing with gases and its introduction and ways that we measure gases. So different quantities that will be used to measure gases and figure out how much of a gas is present in a sample. Okay, so our learning goals are to accurately use appropriate terminology related to gases. For example, pressure, temperature, volume. We'll also look at some standard conditions, temperature and pressure. Okay, and also we'll learn how to convert between different units of a given quantity. Okay, so different units for, say, pressure or volume or temperature. Okay, so firstly, pressure is a measure of the force exerted by a gas over the entire surface area of the container. So it's actually pressure. Pressure is defined as the force over an area, and seeing that we're dealing with a gas, it's the pressure over the entire container. Okay, that surface area there. Okay, so for example, the more collisions that the gas particles make with the container, and the stronger those collisions, okay, the more force that are exerted with the wall of the container, the higher the pressure will be. Okay, so we have a whole bunch of different units. One, for example, a common one is pounds per square inch. That's an imperial version. We also have millimeters of mercury. Okay, not to be confused with the mercury that's used for temperature gauges. This one's for a pressure gauge. Okay, torr is actually another version of the millimeters of mercury. It's identical to it, and it's partially because it was developed by this scientist Torricelli. Okay, kilopascals. Okay, pascals are the standard unit, SI unit for pressure, and basically it is one Newton per meter squared. Okay, that's 1 Pascal. When we're dealing with atmospheric pressure and pressure of gases, we're more into the kilopascal area, so that would be 1,000 pascals. Okay, bars are another one. Bar means, or barometric means, measurement of gases, so it makes sense that this would be the name of a unit. And those are basically 100 kilopascals. So again, another way to use the standard international units there, this time using kilopascals. Basically, atmospheric pressure is around 100 kilopascals, so it makes sense that we'd have a unit that's close to that. Okay. Finally, another unit is used in its atmospheres. Okay, so 1 atmosphere is the pressure found at 0 degrees Celsius and at sea level. Okay, and that is defined as 1 atmosphere. So different units that we can convert between. Okay, so basically they're all in terms of the number of atmospheres. So 1 atmosphere is 13.4 pounds per square inch, 760 millimeters of mercury or torr. Okay, also 101.325 kilopascals is 1 atmosphere. And as I said, it's what we'd find at sea level at 0 degrees Celsius. And then finally, 1.01325 bars. Okay, we're just dividing by 100 there. Okay, so we'll just try one example. Okay, I've chosen a difficult one. So we'll look at how to convert between pounds per square inch and kilopascals. Okay. So the idea here is to figure out what the conversion is. Okay, this one's going to need us to go a little bit further, or possibly just a slightly different way. We could do it one way by converting to atmospheres first, then to convert to kilopascals, and that's probably the best way to do it. So 13.4 psi is going to get us to 1 atmosphere, okay? And then after that, we're going to have to go to how many kilopascals. Okay, so 101.325 kilopascals is an atmosphere. So there's really two steps here. So this is proportionality. So we're just going to take a look at these numbers, okay, and figure out what do we have to do to this number to convert it into 1. Well, and usually it's either division or it's multiplication. Well, this number is decreasing, so it's going to be division. 13.4 will get us to 1, okay? And then in the next step, what are we going to have to do to go from 1, this value 1, to 101.325? Again, it's either multiplication or division. This time the number's getting larger, so we're going to multiply by 101.325. Okay? That will get us all the way to kilopascals. So we got to do these two conversions. So we'll take our 90 psi, we'll divide by 13.4, and then multiply by 101.325. And that'll give us our kilopascals. Okay? So 90 divided by 13.4. If we just needed to stop there and get atmospheres, that's how many atmospheres we'd have, 6.72. We don't have to. I'm going to leave my value in the calculator and multiply by 101.325. And I get my number of kilopascals, so it's 680.5 kilopascals. That makes about sense too. This is about, I'd say, maybe about 5 to 6 times the size of an atmosphere. So like we said, it was about 6 atmospheres. So we should see a number that's about 5 to 6 times larger than the atmosphere in kilopascals, which happens to be 680.5. Okay? Another way that we could have done this, and I'll just show you this briefly, is called the unit factor label method. Okay? And the reason why I like to show this is it really simplifies things. Essentially, what we want to do is use these factors or these conversions as factors, as multiplication and division. Okay? So basically, we're going to multiply by a fraction, okay, that will remove psi. So psi is down on the bottom. That will remove them, okay, and change it to kilopascals, okay? And that will leave me with my final value, okay? So if I just look at these, I can actually see it right away. This is 13.4. That's an atmosphere. This is all the atmospheres here is 101.325, okay? Because I've got the psi, these things are equal to each other, so any fraction where you have the numerator equals the denominator, okay? Just like even if it had numbers in there, 2 over 2 or 3 over 3, that's always going to be equal to 1, okay? Because you're taking the number and you're dividing by that same number. These two things aren't the same numbers, but with their units, they are the exact same values. Okay, so that's the idea. And so by doing this, if we think about canceling with fractions and how to simplify some fractions, we can cancel out the psi's and just be left with the kilopascals. And as you can see, what ends up happening is we end up taking, sorry, I don't want to have this one in here. I want to have the 90. Okay, so we end up taking the 90, we divide by 13.4, just like we did, and then we multiply by 101.325. This is the exact same math. It's just everything's contained in this one unit factor label, okay, or unit factor. So it's 90 times 101.325 divided by 13.4. That's going to give me 68.5. Okay, and it's all using the fact that these two things are identical, even though they have different numbers. Their units make them identical. And we're left with this unit here, which remains with the numbers. It's so important to keep those units together. and then the PSI unit is gone. Okay? So they've been canceled out, and the PSI unit is done. Okay, so that's converting for pressure. Let's look at volume here briefly. Okay, so a volume is a measured amount of space occupied by the gas. Okay, usually it's a three-dimensional unit. Okay, so it has 3 dimensions, so cubic meters would make sense. Liters is a form of capacity, which in most cases it's just, it can be used interchangeably. We've also got milliliters. We also have centimeters cubed. That one's a very useful one. It's used for syringes often, so cc's it's actually named. And here are some of our conversions here. So we've got 1,000 milliliters goes to 1 liter. 1 milliliter is 1 cc. Okay, 1 meter cubed. Okay, now this isn't linear anymore. This is cubic differences. Okay, so 1 meter cubed isn't just 100 centimeters cubed. It's 100 cubed. Okay, and you can see what is going on with this. 1 meter times 1 meter times 1 meter is the same as 100 centimeters times 100 centimeters times 100 centimeters. That turns out to be 1,000,000 centimeters cubed. So 1 meter cubed is equivalent to 1,000,000 milliliters. If we change milliliters out, milliliters, there's 1,000 milliliters in 1 liter. We're going to divide by 1,000. We're going to get 1,000 liters. So 1 meter cubed, which is quite a large value, is 1,000 liters. It's not 1 liter. Okay, so just remember that. So we'll look at this example. Again, we can kind of use what we have here. And I'm just going to use a simple method for this. Okay, so 1,000 liters, this one you could probably do in your head, is the same as 1 meter cubed. Okay, what's the math that we have to do to go from 1,000 to 1? Remember, it's either going to be division or multiplication. Well, we're going to divide by 1,000. Okay, so we need to do that with this one. Divide by 1,000. And so 9,000 divided by 1,000 is equal to 9 meters cubed. Okay, and it's that simple. Okay, after you start getting some practice with it, your conversions will be done quite easily. Okay, last quantity that we're looking at with gases is temperature, and temperature is a measure of the average temperature. The average speed. Excuse me. Or average kinetic energy of the particles in the sample. Okay, so it's not the total speeds, it's not the total energy that's present in the sample, it is the average. Okay, so some particles are going to be moving faster, some are going to be moving slower. Okay, there's going to be a lot in the middle range, but there's going to be some fast ones as well, and some slow ones. All right, so just think about that. That it's not doesn't represent the speed of all the particles. Okay, but generally, as the temperature goes up, the particles tend to be going faster. Okay, as the temperature goes down, the particles tend to be a lot slower. Okay, kind of like people too. Okay, when it's cold out, you're moving a lot slower. Okay, you're a little bit more sluggish. When it's warm out, you're moving with a little bit more of a brisk pace. Okay, there's 3 main units here. You're really only going to need to be looking at a couple of these. Okay, generally we're going to use Celsius and Kelvin. For all of our measurements and all of our laws that we're going to use, we're going to need to use Kelvin. Okay, so we don't want to use Celsius because Kelvin's the absolute temperature, and it basically makes all these relationships proportional. Okay, whereas if you use Celsius, because you got some negative values that could happen, you would end up getting negative numbers, and even 0 would be a problem in some of our formulas that we have. So we really want to make sure we're using Kelvin all the time. Almost never going to use Fahrenheit. I'm going to do a couple examples with Fahrenheit, but mostly it's going to be with Celsius and Kelvin. Okay, so we have different relationships here. Basically, you take the Celsius temperature and add 273, or if you have the Kelvin temperature, you subtract 273, because absolute 0 is, and then we can show this here. We have the Kelvin temperature, which is absolute 0. That's the lowest temperature possible. Never been recorded, but it's been approached very closely. If we subtract 273, we're going to get negative 273, and that's absolute zero in Celsius. Okay? So let's just take a look at a couple of these examples. So 44, so we want to go to Kelvin, so we're going to add 273. So adding 273 to this is going to give us 317 in Kelvin. So this one's not a multiplication conversion, this is an addition. Okay? If we want to go to Celsius, we're going to subtract off 273. Celsius is always smaller than the absolute temperature. 83 Celsius. Okay? Finally, if we want to do some of these conversions with Fahrenheit, we need to use the formula that's present. So the formula is Fahrenheit equals 9/5 of Celsius plus 32. Okay? So we're going to plug in our Celsius value. 9/5 of 30 plus 32. That's a little bit higher than room temperature. It's lower than body temperature, but it's about that. So 5 into 30 is divided by 5 is 6. Okay, and what do we have here? So 9 times 5, 9 times 6 is 54, and 32. 86 degrees Fahrenheit. And that's actually a warm day outside, okay? So 86 Fahrenheit is quite warm, all right? If we want to go back from Fahrenheit, we can do that. We'll test it out here. This time what we have to do, we're going to use the formula, but we're going to have to rearrange it. We're going to have to do some rearranging and dividing to get this correctly. So, so Fahrenheit equals 9/5 Celsius plus 32. Okay, so this time we're going to sub this Fahrenheit value in over here on the other side of the equation. So minus 40. Now, I don't want you to be, this is kind of a neat value here. You'll see shortly what I mean. Okay, so I'm going to move the 32 over. Okay, I'm going to subtract 32 from both sides. So that's going to be negative 72 9/5 of C. Okay, this is, I want to do the opposite of this, so I want to multiply by 5 and then divide by 9. So 5 divided by 9, or multiply by the reciprocal. So 9 goes into 72 8 times. So it's going to be 5 times negative 8. And this turns out really kind of neat. It's also negative 40. And this is the one spot where both scales actually match, okay, at negative 40. All right, so that shows us that it's true, and that is the end of our lesson.